Welcome to another episode of Standing on the Shoulders of Giants, and this week we'll be looking at little Pluto and its fall from grace. In a cosmos where we're used to timescales that span billions of years, Pluto has had a fairly short career. It went from discovery to demotion in less than 80 years. Spotted in 1930, Pluto enjoyed mere decades of fame as our ninth planet before being stripped of its status and downgraded to a dwarf planet in 2006. But what happened to merit this? To a casual observer, the decision seems strange, arbitrary, or even downright hostile to the smallest member of our planet team. In truth, the research that led to Pluto's new classification can be tracked back to decades of research on the outer planets and bold new ideas for how planetary systems should work. This program tells us the story of Pluto, its discovery, the discovery of the objects that would one day become its new siblings, and the incredible heroes and scientific missions that continue to study Pluto today. At the start of 1930, our solar system had 8 planets that we knew about. Neptune had been discovered almost a century earlier, in 1846, and astronomers had long since mapped and tracked the orbits of it and the other planets in great detail. Those orbits were the first sign that our picture of the solar system might not be complete. In the beginning of the 20th century, an astronomer named Percival Lowell became convinced that another planet was lurking somewhere beyond Neptune. This idea wasn't a new one. Almost as soon as Neptune had been discovered, astronomers had speculated about where the next planet might be, and the mysterious object had been dubbed Planet X. Slight discrepancies in the orbits of Uranus, Neptune, and some comets suggested there must be some previously unseen mass sitting at some greater distance from the Sun. For years, astronomers had squabbled over the maths, the orbital mechanics, and the predictions of the location of a possible Planet X. Lowell set himself the task of carrying out a methodical search for Planet X using computers. Of course, at the time computers were people, and Lowell's group of computers was led by a young woman named Elizabeth Williams, who led efforts to calculate specific predictions for where the elusive Planet X might be. The search was kicked off in 1905 at the Lowell Observatory, a facility Percival Lowell had founded in Flagstaff, Arizona, and would continue to work at it for nearly 25 years. Lowell himself had no luck and died in 1916, heartbroken that the discovery had eluded him. Years later, in 1929, Lowell Observatory director Vesto Slipher, the same Slipher whose observations of galaxies had led to the discovery of the expanding universe, assigned a new young Lowell employee named Clyde Tomba to the ongoing search. Tomba had grown up on a farm in Illinois and had been eager to attend college. However, shortly after his family moved to Kansas, a hailstorm obliterated his family's crops, and with it his financial means of an advanced education. Instead, he began building telescopes himself and using them to observe and sketch the planets. He sent examples of his drawings to Vesto Slipher, who was so impressed he offered the 23-year-old untrained Tomba a job. With clear talent but no formal astronomy training, Tomba took up Lowell's search for Planet X. The search method was simple but effective, and used a device known as a blink comparator. Tomba would capture pairs of images of the night sky on photographic plates, taken 2 weeks apart, and then place them in a machine that could rapidly swap the two images, creating a blinking effect. If the observations were taken correctly, the background stars would remain unchanged, but any moving objects in the foreground, like an asteroid or a comet or a surprise new planet, would appear to shift position, creating a stop-motion illustration of its trajectory through the sky. In January 1930, Tomba captured several images that revealed a faint moving object. Blinking between them, the object shifted across the plates, showing the telltale motion expected for a ninth planet. Tomba had found Pluto. The discovery sparked immediate excitement and enthusiasm from the public and kicked off a long and distinguished career for Tomba, who went on to earn astronomy degrees from the University of Kansas and teach astronomy at New Mexico State University. However, the discovery also sparked surprise and confusion from the astronomical community. The many predictions of a ninth planet seemed to have been proven right, but Pluto was not the ninth planet they'd been expecting. For one, it was far too small. Astronomers immediately realized that it was much less massive than it would need to be to explain the supposedly weird orbits of Uranus and Neptune. And we know today that Pluto is about 500 times less massive than the Earth. Put another way, it's less than 20% the mass of our Moon. Pluto's orbit was also odd, more eccentric and tilted than that of the other planets. The ellipse of Pluto's orbit is so oblong, in fact, that Pluto sometimes crossed inside Neptune's orbit. Between 1979 and 1999, Neptune was actually farther from the Sun than Pluto. Almost immediately, astronomers began wondering whether Pluto was indeed a planet or just a really large asteroid at a surprisingly large distance from the Sun. Tomba himself considered the possibility and continued searching beyond Neptune for years, hunting for other Pluto-like objects. Still, after searching for years and finding nothing else like Pluto, he concluded that it was in fact a planet. In later years, improved data of Uranus and Neptune's masses and orbits led to an update of the calculations that Percival Lowell had used to demonstrate the existence of Planet X. Astronomers today don't see any evidence that Planet X exists, at least as Lowell had imagined it. Still, Pluto's discovery remained, and for decades afterwards it became a focus of research as our new and weird little ninth planet. Pluto certainly seems to have many of the trappings of a classic planet. In 1978, astronomers discovered Charon, Pluto's first moon, and 4 more moons have been found since. Pluto also has an atmosphere, though its discovery proved a bit trickier. The study of Pluto's atmosphere and its place in our solar system is where astronomer Gerard Kuiper enters the story. Kuiper was born in the Netherlands and carried an early enthusiasm for astronomy into his studies at Leiden University. After Leiden, he moved to the United States, working at several premier American observatories of the era. In the 1940s, Kuiper used a telescope in Texas to search Pluto and some of the other solar system's largest moons for any signs of an atmosphere. His observations uncovered an atmosphere on Titan, Saturn's largest moon, but were inconclusive for Pluto. Several years later, Kuiper wrote a paper in which he speculated that Pluto might be a member of a disk of small bodies circling the Sun at distances well beyond the orbits of the other planets. However, he also assumed that Pluto, which astronomers believed was nearly Earth-sized at the time, would have disrupted and scattered these other small objects, leaving no remnant of that disk behind. The idea wouldn't be seriously revisited for several decades. Kuiper himself went on to do years of exciting work on planetary science, carrying out searches for asteroids, studying binary stars, discovering moons of Uranus and Neptune, and working alongside lunar geologist Gene Schumacher on the Apollo program. He was a professor at the University of Chicago, and included one of his PhD students in his work on lunar exploration, a young man called Carl Sagan. Kuiper also pioneered a subfield of observatory astronomy that surprises people even today, and one that led directly to the eventual discovery of Pluto's atmosphere: airborne astronomy. To understand airborne astronomy, we need to go back to two concepts we've touched on before: the electromagnetic spectrum and the effects of Earth's atmosphere. We know that visible light and radio wavelength light can pass through the Earth's atmosphere, letting us detect with telescopes on the ground. We also know that shorter wavelength and higher energy light, like X-rays, go bouncing off our atmosphere and are best observed from space as a result. However, there is a middle ground, both in wavelength and in altitude, where astronomers like Kuiper could get a bit creative. Infrared light has a longer wavelength than visible light, but a shorter wavelength than radio. Some shorter wavelength infrared light is able to make it through our atmosphere unperturbed, but at longer wavelengths this light starts to get blocked by our atmosphere. More specifically, it starts to get blocked by the water vapour in our atmosphere. This detail is important because while we need to go to space to leave our atmosphere behind entirely, we don't need to go nearly as far if we just want to put most of the water vapour below us. By the time we reach the altitude of 45,000 feet, the stratosphere, we're above 95% of Earth's water vapour and able to detect a much broader range of wavelengths that let us study infrared light from things like other planets, newborn stars, enormous black holes, and the signatures of magnetic fields. There are several ways to carry a telescope into the stratosphere, including suborbital rockets and weather balloons, but Gerhard Kuiper was one of the pioneers of plane-based airborne astronomy. One early airborne astronomy had a 12-inch telescope mounted in the cabin of a Learjet, peering out of a sealed-off hole in the plane's side. Another early airborne observatory, the Galileo Airborne Observatory, was a modified Convair 990 aircraft with additional windows mounted along the ceiling. Kuiper used observations from Galileo to study the clouds of Venus's atmosphere. The technological challenges of an airborne observatory are clearly immense. The telescopes must be mounted so they can capture steady images and long exposures without being jostled by turbulence, and between the aircraft and the telescope a sizable crew is required to safely maintain and operate the observatory. Still, by the mid-1970s, NASA was operating another airborne observatory that could reach the Earth's stratosphere, a Lockheed C-141-A Starlifter, with a retractable door in its rear and a sealed chamber that held an enormous 36-inch telescope. This one was dubbed the Kuiper Airborne Observatory, a homage to Kuiper's advocacy that airborne astronomy held a key to reaching a new part of the electromagnetic spectrum and answering new questions about the planets in our solar system. This proved incredibly true when it came to Pluto. A fly-on observatory has an additional perk beyond its ability to reach the stratosphere: it can move. This meant astronomers now had a top-notch telescope that could be brought to the northern or southern hemisphere and could chase phenomena that might only be visible from specific spots on Earth at specific times. This might sound like a niche capability, but pause for a moment and think: have you ever driven anywhere to see something in the night sky? If you answered yes, then you might be thinking of the total solar eclipse that was visible across much of the United States in 2017. When the moon passes directly in front of the sun and blocks its light, the resulting solar eclipse is only observable across a narrow curved strip of the Earth's surface, following the path of the moon's shadow. Solar eclipses are the most spectacular example of this phenomenon, but we also see similar effects when studying transits when a planet like Venus or Mercury passes in front of the Sun, or during occultations when a planet or asteroid passes briefly in front of a star. But just like eclipses, these events have narrow paths dictated by the shadow that the foreground object is casting, and just like eclipses, these events don't last very long. Some last mere seconds. Still, for a planet like Pluto, an occultation is by far the best way to study it. Pluto reflects very little sunlight, but if it passes directly in front of a background star, we can monitor the star's light curve and use the change in its brightness with time to suss out things like Pluto's size, shape, and whether it has an atmosphere. Picture an atmosphere-less Pluto passing in front of a background star. You'll see the star looking nice and bright, and then its brightness will abruptly plummet as the edge of Pluto obscures the star. If you wait a few moments while Pluto continues to move, the star will then quickly re-emerge as soon as it's revealed by the other edge. Now picture this same process if Pluto does have an atmosphere. The edge of the planet won't be a simple rocky one. It'll be fuzzy, diffuse, blocking the light of the background star imperfectly and leading to a more gradual disappearance and re-emergence of the background star. Astronomers knew that this was the way to definitively determine whether Pluto had an atmosphere, and the mobile capability of the Kuiper Airborne Observatory meant that it could fly into the path of Pluto's shadow as it blocked a background star. These were incredibly complex observations. They depended on a perfect understanding of Pluto's orbit, meticulous monitoring of the occulted star, and the immense skill on behalf of the pilots and crew that needed to get their flying telescope to exactly the right spot at exactly the right time to within a margin of error of only seconds. But in 1988 they succeeded. A team led by astronomer Jim Elliott captured an occultation, including a gradual decrease in the brightness of the background star as Pluto slid in front of it. The data was conclusive. Pluto had an atmosphere. Unfortunately, by then evidence was starting to mount that, while Pluto may have an atmosphere, its status as a planet looked a bit more complicated. If Gerard Kuiper's name sounds familiar to you, it might be because you associate him with the Kuiper Belt. The Kuiper Belt is a wide ring of small rock and ice objects orbiting the Sun. The ring begins just past Neptune and stretches to more than 90 billion miles away from the Sun. In short, it's right in Pluto's neighbourhood. The belt may be named for Kuiper, but he wasn't the researcher who predicted it. That distinction goes to Julio Angel Fernandez Alves, a Uruguayan astronomer. In 1980, Fernandez published a definitive paper studying the orbits of comets and noting that they must be coming from somewhere relatively nearby in solar system terms. His data suggested a belt of comets and other rocky and icy objects sitting precisely where the Kuiper Belt lies today. Other astronomers simulated the motion of planets and comets in our solar system and agreed. There must be a new collection of faint and distant objects waiting to be discovered at the outer edges of our solar system. Clyde Tomba and his colleagues had imagined this possibility decades earlier, but now orbital maths demanded that the Kuiper Belt had to exist. By the early 1990s, research was underway to find the first evidence of this belt. Astronomers David Dewitt and Jane Liu hit pay dirt in August of 1992. They may have been working more than half a century after Tomba and using far more advanced observatory technology, but the blinking technique was still the best method for finding moving objects. For Dewitt and Liu, this meant taking a series of 4 images and blinking between them, catching enough data to track any new object's motion and determine conclusively whether it matched the predicted motion of a Kuiper Belt object. One evening of observations, they blinked the first 2 images in a set and spotted a compelling candidate, a small new object moving slowly across the night sky. The slowness was key, since orbital speed is determined by a combination of mass and distance. Slow motion meant an object was likely pretty far away from the Sun. Something speeding through their blinked images was probably just a nearby asteroid, but a slow-moving object was almost certain to be further away. This is the same principle you see when observing an aircraft off in the distance. That same aircraft flying closer would appear to be moving much faster than when it's farther away, when it can seem to move at a relative crawl. Jewett and Lou kept watching their strange new candidate object, taking the third and fourth image and then continuing to track it for the rest of the night to gather as much data as possible. In the end they were able to confirm what they'd found: the first official member of the Kuiper Belt, an object known today as Albian, that's about 70 miles across and 4 billion miles from the Sun. After Jewett and Lou's discovery, the study of the Kuiper Belt objects exploded. Today we estimate that there are 35,000 objects as big as Albian, or even bigger, in the belt. In the following years, some of these searches became highly automated, with robotic telescopes automatically capturing repeat images of the sky, and software that would simulate blinking images and pass along anything that looked enough like a moving object to a human expert. Astronomer Mike Brown was examining one dataset like this in 2005 when he came across a surprisingly bright and slow-moving object. He recognized that his survey had found a new Kuiper Belt object, and that it was enormous. The object, later dubbed Eris, was the largest Kuiper Belt object ever found at the time, at least officially. Where did Pluto belong in all of this? Mike's Brown discovery of Eris put Pluto in an awkward position. Eris was thought to be practically identical in size to Pluto. Did this mean that Eris was now our 10th planet? What about Albian, and the heats of the other objects in the Kuiper Belt? Were some of these planets too? Pluto certainly seemed to be a member of the Kuiper Belt. Did this preclude or damage its classification as a planet? What exactly was a planet anyway? This last question was the subject of an infamous vote carried out in 2006 at the meeting of the International Astronomical Union. Astronomers realized that a clear definition of what constituted a planet was long overdue, and a number of experts weighed in on proposed criteria for what we might call a planet. A proposal drafted in part by Julio Fernandez, the astronomer who originally proposed the Kuiper Belt, gained traction, and after intense debate a vote was held to approve an official definition for a planet. A planet, astronomers ultimately agreed, had to meet 3 criteria. It had to be orbiting a star, it had to be massive enough to hold itself together with its own gravity and assume a roughly round shape as a result, and finally it had to have cleared its neighbourhood, gravitationally dominating its orbit and kicking out any other objects of comparable size that weren't tied to the planet itself as companions. Pluto was orbiting the Sun, and it was plenty round, but critically it had not cleared its orbit. Its orbit was in the now cluttered Kuiper Belt. Astronomers voted, the vote passed, and Pluto was demoted. According to the newly approved definition, Pluto was no longer a full-fledged planet, but a dwarf planet, joining Eris and other large members of the Kuiper Belt. The news made international headlines and prompted a flurry of editing as Pluto was removed from lists and textbooks and solar system dioramas in classrooms across the world. Some astronomers objected, and still object today, to the classification, arguing that the definition was arbitrary or not properly considered. As with the recording of this program, the status of our solar system stands. 8 planets have been discovered from Mercury to Neptune, and Pluto is one of a handful of dwarf planets. It might be easy to be annoyed by this decision, and to see it as losing Pluto from our list of planets. However, a more accurate description might be that we've gained a fleet of dwarf planets, and a fascinating new region of our solar system to study and explore. Incredibly, we have actually gotten the opportunity to explore Pluto close up. The New Horizons mission was designed with the specific goal of flying past Pluto and giving astronomers the closest look yet at the solar system's first dwarf planet. New Horizons left Earth in 2006. Pluto was actually demoted during the trip and reached the dwarf planet in July of 2015. Even after almost a decade of travelling through the harsh environment of our solar system, the space probe worked wonderfully. Images sent back to Earth as New Horizons approached and flew past Pluto revolutionised humanity's picture of the dwarf planet, revealing its surface in exquisite detail for the first time. One famous image showing what looked like an enormous heart-shaped smooth patch on Pluto's surface was immediately copied and pasted into the headlines and memes. The heart was eventually dubbed the Tomba Regio, in homage to the astronomer who had first spotted Pluto so many years earlier. New Horizons flew onward from Pluto and travelled past another Kuiper Belt object, Arakoth. Today astronomers continue to study Pluto and the rest of the Kuiper Belt, peering into the outer edges of our solar system to understand how these rocky and icy objects formed and what they can tell us about our planetary neighbourhood's history. Next week we'll turn our attention from these far reaches of the solar system to the centre and explore what we know about our own sun. Well, old Father Time is tapping me on the shoulder and telling me I've got to move over and make room for somebody else. So as always, please everybody stay safe, look after one another, and I'll see you again next week. Bye for now.